in one or the other aspect. So there was this question about how long does it take for the myosin to go through the whole cycle? And I said milliseconds, okay? But this is only the fast part of the cycle, the power stroke. And then it actually goes away from the filament. It's repriming, okay, the recovery stroke, and this is a slow process. This is actually coupled to ATP hydrolysis, and it's really the rate-limiting step. And this is much slower. So the cycling time for myosin is more like 100 milliseconds. Not 1 millisecond, okay? And this is also interesting in the light of Mike's talk, because Mike talked about this crossover between passive and active fluctuations. For example, ion channels, membranes, beating flagella or whatnot. And here you see that the typical time for these mechanoenzymes to work is sort of sub-second, okay? So you would expect the crossover to be around 1 hertz, 10 hertz or something like this. And that's exactly what they measure, as far as I know, okay? So it fits very nicely with this idea that everything which is faster than this is more passive fluctuations. And if it's slower, it could be active fluctuations. And you can show it by violation of the fluctuation dissipation theorem. And the second aspect I wanted to come back to is this dissociation rate. So there were some questions by Leon yesterday, and I answered very badly because I tried to remember what you do in Kramer's theory and how you do it. But there's a very simple argument here, okay? So the dissociation rate, this is the K off, which is also in one of the exercises. It is basically some attempt frequency and then the Arrhenius vector. So it should be e to the minus delta E divided by KBT. This is the barrier height. And now if you think about the effector force, so this is some energy landscape here, and this is the delta E. And now if you actually come with a force, you basically lower this by tilting it down, okay? So basically what you would write is E minus A times F times X, if you wish. And then if you actually, no, let's put it like this. So this is the distance here between the minimum and the maximum. And if you put this in here, then you just give this another name here, okay, the initial barrier. And then you have this e to the plus F times A divided by KBT. Because the barrier height is the initial barrier height minus what you bring down by the force, okay? And this way, it's very easy to understand why you get this factor in the dissociation rate. So there's an exponential increase in dissociation if you increase the force. And if you are in this, there are many more complicated calculations, okay? But this is the limit of an infinitely localized barrier. So the barrier the barrier position does not change as you apply the force, okay? In reality, you have an extended barrier with a certain width, and then as you apply force, the position changes, and these are the calculations which have been done by Olga Dutko, Gerhard Hummer, Udo Seifert, and so on, but we don't really need this, okay? So just as an explanation, this is the better explanation than what I gave yesterday. Okay, now we come to the subject of today, and this would be viscoelasticity, because what we learned yesterday, both in my lecture and the one by Lisa, that we basically have two important states of matter, okay? We either could have a solid, and then the stress would be the Young's modulus times strain, or we could have a fluid, and the stress would be some viscosity times the strain rate, okay? So this is called a Newtonian fluid. You can call this a Hookean solid. And these are our two very fundamental material laws or constitutive relationships. Now the question is, if you go to biological systems or soft matter systems in general, we know that they have to be combined into something more general, okay? And this is viscoelasticity. Okay, so viscoelasticity has a long theory. It's a very mature field. Goes back to people like Maxwell and Boltzmann in the 19th century. And here I give you a very gentle introduction into the basics of viscoelasticity, and then we will use it for our models for adhering cells. So the first thing we have to understand is that if you start combining these systems, you still have to make a clear statement if in the long run it will be a fluid or solids, because it's just two different things, okay? I mean, you cannot, there is nothing, I mean, it's not that viscoelasticity is just in between, but there, in the end, there has to be a clear structure in the system such that it either stays rigid or it's floppy, okay? Or it's actually plastic or flowing. So there's no way around somehow specifying this. And this means that we have two fundamental types of viscoelasticity. And we are now going through them. So the first one would be a viscoelastic fluid. Which means that we make a decision that on the long run, it's still a fluid, okay? So it will never stop relaxing somehow if I pull on it. And that's the famous Maxwell model. And it's simple. What we do is we actually take a spring, which is our Newtonian, our Hookean solid. And then we take a symbol for a fluid, which is this dashpot, okay? So the dashpot, we all know from cars, okay? It basically damps the momentum in the car. And of course, in the car, it would be some kind of oil or something like this. So that's why we use it here for a fluid element. But there's something really weird about this element is that in principle, it can give out infinite amounts of material, which is unphysical, right? But the symbol of the dashpot means I can pull, I pull out lengths, it will never stop, okay? And this is, of course, an unphysical aspect of the system. So we have to be careful that we're not running into this sort of artificial aspect of the system. And then we pull on this with a force couple. So it's a mechanical test I talked about all the time yesterday anyway. And now we have everything to write some equations. So I call the force, which is in the spring, Fs, the force, which is in the dashpot, Fd. Then I have a strain in the spring and have a strain in the dashpot. And because I have arranged them in series, the strains add up. And the forces are the same. So the force in the spring is the force in the dashpot. It's just the given force which I pull, okay? And the overall strain of the two strains and now we actually go to our constitutive relationship. So basically, this is the solid part. Then we go here, okay? And strain is stress. So now it's a one-dimensional system. So it's force divided by Young's modulus, which I now call C, okay? So the C is the one-dimensional modulus. And if you look at the dimensions, you see that the C should be something like E times A. So it should be the Young's modulus times cross-section, because we basically think of a long slab of material with a cross-section A, and we go into a one-dimensional description. So we have to convert the three-dimensional Young's modulus into a one-dimensional property, and therefore we have to multiply with the perpendicular direction, which is the cross-sectional area. Okay, so what I have in mind is basically a slab of certain shape, could be quadratic or could be spherical, and I'm pulling on this, and it has a Young's modulus E and has a cross-sectional area A. Okay, so this would be my first constitutive relationship for the spring. Now comes the dashpot, then I go here, okay, and then I see it would be force divided by viscosity. Again, I do the same thing. I convert three-dimensional viscosity into some one-dimensional viscous coefficient. And sorry, no, that's fine. I'm missing the dot here. So what I have to do is basically, wait, this was the wrong way, sorry. Yeah, someone should correct me if I'm making the stupid mistakes, okay? So, no, wait, so I have to start from scratch. So what I do is, okay, let me start again. So first thing is I write the strain is the sum of the two strains, right? Then next step is I look at these relationships and I see that here I have a dot, okay? So this is the problem. So what I now have to do is I have to dot both sides, okay? And then I also dot the F, this is divided by C, and then here it's just F divided by C eta. And this should be the constitutive relationship. Okay, so yeah, to get the final equation, I bring this to the other side. So I multiply with C, then I would have F dot in the front. I would have the combination of C and C eta. You see that the cross-sectional area drops out again, and I basically get the relaxation time, which I defined before. So I will get 1 over relaxation time times F. This makes a lot of sense because I have to offset the derivative here with 1 over time. And on the right-hand side, because I multiply with C, I get C times strain dot. And this would be now my overall law. So you see, the nice thing is that I managed to get rid of spring and dashpot, okay? They disappeared from the equation. The equation is in itself closed. It's just the force acting on the element and the strain, the overall strain of the element. That's it. Okay, so it's a nice relationship. You see, it's an ordinary differential equation. For F, it has first derivative and F itself. For epsilon, it has only first derivative. Okay. So in experiments, you now can go 2 ways. So maybe I should write this on the next blackboard. So you have this equation, and now there are 2 types of experiments, or you could also say doing the analysis. You could either fix the right-hand side. So this means you basically give the strain some function of time, and then you solve for the left-hand side, okay? So then you basically get F as a function of time, and this is called a relaxation experiment. Or the other way around, you fix the left-hand side. So you fix the force, and you basically ask, how is the strain developing in time? And this is a creep experiment. Okay, so in principle, we can go through this. So let's first do the relaxation experiment. So then we get this F of t. And if we do it with a step in the force, we would actually get a so-called relaxation function, which often is called, not here, it's often called G of R, I think. So we just keep df. So the idea is that you have to solve this equation over there with the right-hand side given. Okay, so it's an ordinary differential equation of first order. And you do it by actually writing that the overall solution is the so-called homogeneous solution plus a particular solution, which means for the homogeneous solution, you put the right-hand side to 0, okay? And you ask what the solution is. And obviously, this will be an exponential function. So let's say this would be a jump to F naught. And then it should go, or you start with F naught, and then you should go down with e to the minus t over tau. Okay, so this solves the right-hand side if the left-hand side if the right-hand side is 0. And then to get the particular solution, you do it by variation of the constants. So you basically take this guy and put in a t-dependence, you put it back, then the homogeneous part drops out by construction, and you get one new equation. And then you actually solve this one. So it will be, yes, let's write this. If you put this ansatz with a t here into this equation, you would get that f naught dot should be c times eta dot e to the power of t plus tau. And then you can integrate this up. And the particular solution will be an integral. It goes with the elastic constant integral over some auxiliary variable from 0 to t, e to the minus t dash divided by tau times epsilon dot at some time t. Okay, so these are the kind of equations which are called linear Boltzmann, Maxwell-Boltzmann or something like this. Okay, so this is the theory of viscoelasticity. So this is basically a kernel which you have to integrate. Sorry, yeah. Thanks a lot. Okay, and with this, we basically have the solution because the full solution is just the sum of the two, okay? And the next thing is we have to put in initial conditions. So we take an example. So we take a strain ramp. So as a function of t, I ramp the strain up in a linear fashion. So I give it a slope r. And at some time, let's call it t naught, I'm basically keeping it constant. Okay, so I'm pulling on something and then I leave it constant. And I'm not pulling with a constant force, but I'm pulling with a constant strain. Okay, something which is easy to do if you have a piezo, you just program it to pull, pull, pull. Okay, irrespective of the force it's creating. Okay, and then you basically can solve for both parts. The trick is it's a differential equation with no memory, okay? You can basically start at any point and integrate from there, right? So we can just integrate from here to some point here. And if you want this part, we just integrate from here to that part. So what you get is for time smaller or equal t naught, so for the ramp part, we would have this integral, which I just wrote. So let me really go step by step here. Yeah, so the first thing you see is that we actually start from 0 here, right? Strain ramp. So we cannot use the homogeneous solution, but because the homogeneous solution should start from some finite value. So this is gone by initial conditions. So we only can use the particular solution for this part here, because we start from 0. Later, it will be exactly reverted, okay? Then we have the integral, I just copy from here, we have c. Now I have this from here, I basically have this r, the rate with which I'm pulling, this is this r which I have defined. Then from this exponential, you can take it apart and pull out the first one, so you get e to the minus t over tau, and then comes the integral. So this is now e to the power of plus e tau, t dash over tau, t d dash. Okay, from 0 to t. And this means that you get 1 minus e to the minus t over tau. Okay, and there must be a 1 over tau in front. Okay, so you also get this factor here. Yeah, and then in principle, you can combine this guy with this guy. This gives us the C naught. But otherwise, no, we don't need to do this. Otherwise, it's fine. Okay. So, so what I'm saying here is that this part is this part here. So you basically get C times R times tau times this function here, okay? So this means if I now try to draw this here, I could use another color, okay? We basically have a function which looks like this, okay? So we start off linearly. If you actually look here and you make a Taylor expansion for small t, then the 1 goes away. This tor here cancels this tor, and you see that you basically start with c times r, okay? So here, this part is elastic. It's c times r. And then if you go for very long times, this basically goes away, okay? Then you have this guy times this guy is the c eta times r. So you basically have a plateau here at c eta times r. And this is viscous. Okay, so what happens here is that as you pull the Maxwell chain, this, yeah, 1 second, as you pull this guy, okay, in the beginning, you actually stretch this spring here. This is the elastic response. Then the spring is extended to some extent. It doesn't extend anymore, but you pull out lengths from here. And then you would go infinitely with pulling out lengths from here, okay, with a constant strain rate.
About F naught, like if we plug the whole solution for F, yes, the epsilon is 0 at time 0, but you have derivatives, so like. Here.
I will discuss something like this later. Yeah, so there's a way you can look at this. Yeah, but from the physical intuition, it should also be clear that this has to be the solution, right? Yeah, because you have to start from 0. Yeah. We'll show you in a minute how one can look at this. Yeah. But first, I want to finish this part here. So this is what we now found for the ramping part. Okay, now we go into the plateau phase. So now we go for t larger than t naught. Yeah, in this case, the epsilon naught is the epsilon dash is 0. Okay, I'm in the plateau, no strain rate anymore. Therefore, this particular solution, this one, is 0. Okay, this is 0. So the integral is gone. But we have our homogeneous solution. That's exactly the situation where the homogeneous solution kicks in. Okay, and therefore the f of t will be just the force which I have reached at this point here. So this is basically, I mean, I have to put in the values in this solution. Okay, so I put in t naught. This gives me some value, some f naught. But if you wait long enough, it's basically close to this value here. And then from this one, you actually decay down. But you start the decay at t naught. Okay. So this means that I now have to continue like this. There were some color chalk here. So maybe these things I can do with color. So this is basically how the system looks like. Okay. So again, as you first pull the spring, then you pull lengths out of the dashpot, then you stop pulling and the force goes down because the spring relaxes and there's no pulling anymore. And the dashpot basically brings it down to 0. Okay.
What is a F naught dot mean exactly? So T particular from, what does that stand for? The initial derivative of T0 force or?
So wait a sec. Yeah, so basically what you do is you take this sum and put it in here. But so the homogeneous solution, so I take the ansatz f naught of t times e to the minus t divided by tor. Okay, so this is what's called the variation of constants. So this was a constant in the first calculation. Now I say it's a function. Okay, if I take this ansatz and plug it in here, then the terms which are from the homogeneous solution go away, and the new term, which was not possible before, would be the f dot, right? And that's why the why you get a differential equation, which is f naught dot equals this, and then the solution would be the integral. Okay, sorry, I'm always pushing too hard here. So in cell mechanics, we often use this Maxwell element. If we know that basically the system is flowing in the long run, okay? So maybe cortex, laminar podium, systems like this, which are really turning over a lot, okay? And if I'm now pulling on them internally or externally, I can use the Maxwell element. So the simplest idea to actually do this would be to introduce what I call the active Maxwell element, okay? So the active Maxwell element would look like this. So I take a normal Maxwell element, like before, okay? And in parallel, I introduce some pulling force, okay? So there are different symbols in the literature, and of course, I like the symbol which I invented. I'm not sure if I really was the first one to invent a symbol. But what I do is I do it like this, okay? This is basically myosin motors pulling between two actin filaments, right? But if you look in the literature, people have used this concept long time before, okay? And one symbol which you sometimes see is in the ion channel community, okay? People also have active elements. Something is pumping charges, okay? And they use this sort of voltage gate. And I've seen this also for myosin, that people use this symbol, okay? Like Joe Howard, I think, uses it. And there are all kinds of other symbols you can think of. But this is my favorite symbol. Yeah, maybe you want to represent myosins like this, okay? Then you could draw it. But I think for me, it's convenient to draw it like this, okay? So this would be active cell mechanics, a Maxwell element in parallel with some myosin motors pulling. But if you think about it, so let's call it F active, and we say it's constant because it usually goes with the chemical potential, and the chemical potential is constant, right? This is the concentration of ATP, ADP, and PI, so it's typically a constant value. Now, if you think about this, this is actually, also I call it active. It's completely trivial. It's just a force pulling on the system, okay? But what's a little bit strange here, it's actually a compressive force, right? Because I position it in parallel to the passive, and it's pulling together because myosins are always contracting. So it's basically the same thing, like going back to my original Maxwell element, spring and dashpot, but now pushing on it, okay? So it's really like compression. Now you see the problem with this is that this is not really stable. Because we just discussed what happens in a Maxwell element. You can pull out infinitely large amounts of material. If you compress, you can push in infinitely large amounts of materials. Okay? And the motor is pushing all the time with a constant force. So this model is nonsensical in a certain sense, okay? But still, it's a good model if you put it into a context where it's balanced by other forces, right? So if you do a tissue type or, tissue level or cell level model where this active Maxwell element is balanced by other forces, then you just have a little bit perturbation around this, right? Because something else is pulling from the side and then it's stable again. I just want to point out that if you think about it, you're a little bit confused, because you think, okay, this is a nice model, but it's not stable because it would basically, like a black hole, eat up all the material in the system, okay? So that's why it's a little bit strange, but in principle, it's a completely good model if it's used in the right context. Okay, so for completeness, and also because this question came, let me briefly discuss the creep function. So in the creep function, we fix the left-hand side. Okay, so what we do is we do a force jump. So if this is time t, let's say at t equals 0, I ramp up the force to a certain value, let's say force naught, F naught. Okay? Now comes the problem which you ask about, namely, how do we deal with the boundaries if there's something happening at a boundary? And there's a nice little trick how we deal with this, okay? So what we do is we go back to our differential equation and we rewrite it in differences. So rather than using differentials, we use differences, okay? So rewrite our ODE, ordinary differential equation, in differences. So first thing I have is, I have the derivative of f. So this is f at time 0. So I should write around t equals 0. So we only look at what's happening at the beginning because this is where it's pathological. You have to jump in f, okay? So first thing we have on the left-hand side is the time derivative. So I write this as f at the position 0 plus, okay? So this is here on the right-hand side, minus f at the position 0 minus. So this is here at the left-hand side. And I divide it by delta t. Yeah, and actually what I also do is I multiply everything with Tor. So the 1/4, I actually bring it to this term. And then I write the second term, this is just f. So here I do sort of a sensical approximation that I write it as the average over left and right. Okay, so I basically take this value here in the middle, something you would also do for Heaviside step functions. Okay, you also usually take the 1.5 term. And then on the right-hand side, I have c, I multiply it with Tor, and I have the time derivative of epsilon, so I write the same thing, plus, minus, minus, divided by delta t. Okay, so this would be my ODE in differences if I go exactly at the point t equals 0. And what I now do is, of course, I multiply this through with delta t. Okay, then basically it goes away here and here. And it will multiply this part. Then I send delta t to 0, and then this will go away. Okay, so it doesn't even matter if I put 2 or not. Okay, it doesn't matter because this goes away anyway. Then the force at the left-hand side, this will be 0 because I start with 0 force. So I only keep the force at the right-hand side. And the same thing here, this is also 0. Before I start stretching, there's no displacement. And then you see, this is too small for me, okay. Then you see what we get is that the force at 0 plus, so right after the force jump, should be c times epsilon 0 plus. Okay, it's the only term which stays. It's basically this term and this term. Okay, and the Tor drops out because it's on both sides. So I get this, and this is exactly the elastic behavior. Okay, so this means that what happens in the very first moment is with a force jump, you stretch the spring exactly to its extension as if there was only a spring. The reason is simple, because the viscous part has no time to react, okay? And viscosity needs time. But because I do this in infinitely fast time, it only can jump to this extension. Yeah, and then the answer to your question is that I could do the same analysis also for the other situation. Yeah. And after that, it would actually, the spring is basically taken care of. The rest would be elongation. Okay, so from here on, you would just elongate. So the overall creep function should be, so the creep function is the epsilon, so the strain, but normalized to the force jump. Okay, so we normalize the amplitude out. So it would be 1 over c, this is the elastic jump. And from there on, you would increase with t. So chalk, color. So basically how it would look like, it would jump up And then from here on, it would go like this. This is the creep function. Okay. So this is actually all I wanted to say about the Maxwell model. There's one interesting thing here. If you think about this, I have solved the same differential equation twice, okay? Once by fixing the right-hand side, once by fixing the left-hand side. And you might ask the question, shouldn't this be equivalent? It's the same equation, right? So, and the answer is yes, actually. So yeah, so the creep function and the relaxation function are equivalent. All the information about the model is in both functions, okay? So both functions carry the same information. And there's a very general relation between them. So if you take the relaxation function, I didn't give it a real name. Okay, let's just take it, call it T. And you take the creep function and you convolute them, you will find that this is T. And this is one of the exercises I gave you. Okay, so you have both functions. You have this function and you have this function. You have to multiply them, convolute them, so do the integral, and then you should get T. Okay, and this shows that basically the same information is in both. But it's not a linear, easy transformation. Okay, you basically have to solve this Fredholm integral equation, which is not trivial, right? So of course we never will use this, right? But we will have a situation where we either need one or the other, and then we will calculate it. And I just want to make this theoretical point that in principle we have solved the same equation twice. Okay. Now on to elasticity. So this was the viscoelastic fluid. And now we do the viscoelastic solid. Two camps here in thermal mechanics, the fluid camp and the solid camp, and I belong to the solid camp. Because I usually care for situations where the cell seems more like a solid, okay? And of course, my favorite example is traction force. So you put a cell on a substrate, it contracts the substrate, and if it was flowing, if everything was flowing, okay, you saw the relaxation function, it should go to zero, okay? But it's not. The cell is sitting on the substrate, and it keeps a certain strain in the substrate, and it sort of reaches a limit where it basically can keep stress in the system, and this is what a solid is doing, okay? So for me, if I look at adherent cells, I see a solid, actually a viscoelastic solid, okay? But if you actually do laser cutting experiments, or if you look at the lamellar podium, if you look at cell migration, and this is what we do later, okay, in the third lecture, then you probably want to take a Maxwell model because things are flowing all the time, okay? But in the context of cell adhesion, we often use this sort of elastic, viscoelastic solid, okay? Now this is now called the correct model. Going back to Lord Kelvin himself, actually it's amazing, but all of this continuum mechanics, so here's the Maxwell model, now we have the Kelvin-Voigt model. Maxwell, Kelvin, okay, it's all Cambridge and Oxford in the 19th century. Also Stokes, Reynolds. So they invented basically continuum mechanics. Okay, so the viscoelastic solid, I think it's easy to anticipate how this will look like. You basically take a spring and you arrange it in parallel to the dashpot. Okay, now if you pull on this with a certain force, obviously in the end, the spring will hold it and there will be always a counterforce. Okay, while in the other situation, in the Maxwell model, this will flow, it gives out length. Okay, in this model, it only gives out length to a certain extent and then the force spring takes over. Okay, so this is why it's a solid. Now, if you look at the analysis of this, it goes completely the same line we had before. But of course, there's one big difference. now the forces are in parallel and not in series. So basically the overall force is the force in the spring plus the force in the dashpot. And the strains are the same, okay? So the strain in the dashboard and the strain in the spring is the overall strain, so I don't have to care about strain really. Then I take the constitutive relations of both of them. So it's simple. The force is the elastic constant times the strain in the elastic element and the viscous coefficient times the strain rate in the viscous part. Okay, and there we go. So it again is a ODE. No reference anymore to spring or dashpot. We just have overall strain, overall force. It's exactly like this equation, except that F and epsilon have exchanged their role. Okay, so it's like the Maxwell model. But F and epsilon are interchanged. Okay, which means that we can immediately write down the solution. Yeah, so basically you have the same integral solution. We don't need to write it. The same methods, basically everything is the same except force and strain now have different roles. So let's quickly look at the creep experiment. So in the creep experiment, we do force jump. So this was the J, which we calculated over there. And you basically write now epsilon of T divided by the force amplitude. Yeah, and then it's basically this integral. So we start from zero strain, okay? So it has to start at 0. We don't need the homogeneous solution. Again, we need the particular solution. So it will be 1 over, wait a sec. Yeah, so F naught, which you just had, then this viscous modulus. The time integral, everything like before. And then the force, and the force is 0 up to here, so nothing happens. Then it jumps to F naught. So you basically can pull it out and it will cancel this guy. So I can also cross this out, put a F naught here, and then these guys are also gone, okay? And this just gives me an exponential function. So it will be, wait, and then I, of course, get from the integration, I get a Tor, and the Tor times over this one gives me the elastic constant again. So I get the elastic constant, and then e to the minus t divided by Tor. So if I show this in color, what you basically get for the strain is this type of curve. It's the same functional dependence like we had before for the relaxation, okay? And it makes a lot of sense. You start from 0 strain. So this is strain, or J. You start from 0 strain. Then you actually have a relaxation process which comes from the dashpot. And if you do the expansion, so you can do the Taylor expansion here, right? Then a 1 over C times. So this goes like, so here in this regime, you have 1 over the viscous modulus times T. So this is the viscous part. And then in the end, you basically run into this elastic part. So it will be just 1 T. Okay, and now the damping has died down and the system is held by the spring, bless you. Okay, and then as in the Maxwell model, you can also talk about the active cell mechanics or active Kelvin-Voigt model. And this basically means that I now have 3 elements in parallel. So first of all, I have my myosin motors pulling, then I have the spring, and then I have the dashpot. Okay? Yeah, this is from here. So if you go to t equals infinity, this is gone. And you have 1 over c. And this is elastic. The viscous part, you do a Taylor expansion in small t. Then you get out the t, so it's linear. You get 1 over tau, you combine it with this one, and then you have the viscous coefficient. So this way you see that the linear part is the viscous part, because it goes with this modulus, and this is the elastic part because it goes with this modulus. So these are the 2 limits of the system. Yeah, and as I said, the one-dimensional modulus is just the Young's modulus times the cross-sectional area, and the same for the viscosity. So we basically talk about Young's modulus here. So this is determined by the Young's modulus, and this is determined by the viscosity. Okay, so in active cell mechanics, what we do is, if you want a solid, something which really can keep force for a long time, we just put a myosin force in parallel, okay? And as I said before, this, of course, is nothing else than taking the normal model and compressing it, okay? So when I actually said that this is unphysical, when I said it's unphysical for the Maxwell model, because if I compress it, I push in a lot of length, okay? So stop this. It looks better now, right? Because the spring can keep it, okay? The model is okay because the spring can keep the compression. But last week you were actually instructed on polymer physics, okay? And you know that polymers don't do it. So polymers buckle under compressive load, okay? So the model is fine, but in our context, it's also bad. Because how should a polymeric system do this, okay? So you have to think about how this works. And so compression is in principle okay for technical reasons, but the compression, I mean, the compressive spring, so the compressive spring in biology is a problem, okay? I mean, if I think about this, okay, what in my body can keep compressive, basically the bones. It's part of the extracellular matrix, which comes with gags, for example, lots of counter ions, things like this, okay? But this is not what I'm talking about if I talk about stress fibers and cortex, okay? I don't have a gag matrix or whatnot, okay? So what is doing it? And there are, if you think about it, it's always some kind of tensional element which comes in, but it's arranged in such a manner that it acts like a compressive element, okay? So this compressive spring in biology often is a tensional element. And I think if this sounds strange to you, just let me make a little cartoon what I'm talking about. My example would be muscle, okay? So in muscle, we have the thin filaments. So these are the actin filaments. Then we have the thick filament. So this is the myosin. And as I said, for me, this is a active Kelvin-Voigt model, okay? Because the myosin is pulling here, and I know that the muscle basically stabilize at some position, okay? So if I have to lift something, I know I can keep it, okay? If this was a Maxwell model, it had to go down, right? But it's not. So I have a stable situation. And if you look at the muscle, the way it works is you basically have these set discs here. And then you have one element which is springy, okay? And as you contract, you basically push this element, but it's not in the middle, it's on the outside. So it's actually acting like a compressive element in the middle, but it's really a tensional element out there. And do you know the name of this molecule? The molecule which keeps our muscle stable? Titin, okay? And it also happens to be in stress fibers. So titin, and many other elements, okay? In principle, you have also alpha-actinine and so on. So there are elements which keep the system stable. They're not necessarily acting as compressive elements, maybe more like tensional elements. But in the end, it is actually like this cartoon here, okay? The model is fine. You have to be a little bit creative where you actually position your springs.
Okay. Should I interpret it as a model for actomycin?
Yeah.
Or to what scale can you apply this?
We come to this, but we use it later as a model for contractile cell, but we just make a spring, a chain of these elements. Yeah. So for us, it's one of our favorite models is chain of, and this would be a stress fiber for us. Okay, so how do I clean the board, by the way? Is there some, there's some water too, right? Okay. Good, so as I clean the board, I continue to speak. Yeah, but I don't mind. Let me try it. I mean, I hate just wiping it. So if you think about these models, the problem here is that there's no space in these models, right? So basically, these are models of 0 dimension. So if we, I mean, it's not quite right, okay? There is this strain in the system, but this strain doesn't have a real extension in real space, okay? I don't have coordinates, I just have strains. So the challenge is now to make this model more space-like, okay? So we basically want situations where one Maxwell model is balanced by a neighboring Maxwell model, things like this, okay? And therefore, we really have to now put forward equations which have real space in them. And this is actually the realm of continuum mechanics. So, I see why it's difficult here. So the next section will be on continuum mechanics. But rather than going into 3D continuum mechanics, which we do a lot in my group, I just talk about 1D continuum mechanics. So I talk about bars. And I sometimes call this scalar continuum mechanics because associates. Those are to come in the third lecture. Yeah, I'm sorry that you have to watch me doing this. Yeah, this would be great, actually. Yeah. Okay, some volunteer. This is really great. So I finish this and then you can continue. Thanks a lot. Okay. Was the mic out all the time? Okay, it just made a wrong move. Good. Relief. Okay, so what I want to come to is the cell as a contractile element which is sitting on a substrate. Okay, so what I will have in mind is something like this. I have now many of these active elements, each of them are contracting, so the whole thing contracts. And I want to couple this to an elastic substrate, but it would be too difficult right now to couple it to real elasticity theory. So I make a shortcut here and I couple it to a layer of springs. Okay. So this is what's called an elastic foundation. And the elastic foundation is sort of a shortcut if you want to put some elasticity in it, but you don't want to solve the whole equations for an elastic substrate. And then this here would be the cell as contractile bar. Okay, and the plan is that I manage to go through this model. It will take half an hour, and then I still had some slides. So we'll see how this works out. Good. So the way you analyze the system is very important. It's really the basics of continuum mechanics. So what I now do is, this is my spatial coordinate x, which I now introduce, okay? And then I take a slice here. And this slice has the thickness delta x, okay? And then because the system is one-dimensional, I only care what's happening in the normal to this. So I only care what's happening here in this direction. And I basically assume that there is some stress which is in the normal direction, which has a profile which I call n of x. So it's actually, sorry, this is actually a force. Let me check my notes. Yeah, I do it on the force level. So this is the normal force profile. So these are the forces in the bar. And now I look at this slice here and I make the force balance. Actually, this is a bit weird here. Okay. So the force balance would be that I have three forces. So maybe I take a color again. So I have one force which goes in this direction, one force which goes in this direction, and then I have a force which basically comes from these springs down here. So I have three different forces. What might look a little bit strange to you, okay, is that this here is the normal force. It points in two different directions, okay? But the reason is that we basically normal to a surface, and this normal changes its direction as I go from the left side to the right side, okay? So you have to get used to it. It's a matter of convention in some sense, okay? But we write positive numbers for the force, and we consider two forces which pull against each other, okay? So this is why we give them different, thanks a lot. It's really nice, yeah. So we basically consider these forces working against each other. This is from the springs. So, I mean, these guys here are basically springs. Yeah, we come to this. Anyway, so this is the force on the left-hand side. This is the force on the right-hand side. And now we have the force from the substrate. It's a simple spring. So it will be a spring constant K. And then I introduce a field U, which is the deformation field. So the deformation field is basically this distance here. So this spring, if I remove the bar, this spring would relax back to this position, okay? but it's now pulled to the right-hand side, to the end of the bar, because the bar has contracted, and therefore there is this u of x, okay? And at each point, I have a u, and you also see that u in the middle is 0 for symmetry reasons, okay? So for symmetry reasons, this will be 0. So this will be a positive u, this is a negative u, okay? So basically the u go with some negative values, so 0 to some positive value. And that's it, okay? This is my force balance, very simple. So you see easily what you can do here. Because I make a 1D model. Yeah, so I say a flat cell, no nucleus, okay, just the lower part of the cell, very flat compared to lateral extension. Yeah. So you can see immediately what you can do here. You do a Taylor expansion, okay? Then the n drops out and you only get the, the space derivative of n. So I bring this to the other side. I bring this to the left side. I divide by delta x. And then I basically have on the right-hand side, I have k divided by delta x times u. And this I now give a new name. I call it rho, the spring density. So it's one of these limits where you have to say, okay, this is going to 0, this is going to infinity, but in such a manner that you get a finite value, okay? And it would be the spring constant per length, basically, a spring density. Yeah, and this is my equation. So this would be my force balance. So the first thing you see from this is that that what matters is not the absolute value of the force. It doesn't matter, okay? What matters is the slope, the derivative. And the reason is very simple, okay? If the cell creates huge forces, but they're all balanced locally, it doesn't matter, okay? As long as the material doesn't break, which can happen, as you know, but as long as there is enough stability, it doesn't matter. What really matters to get displacements is if there is a change in force, okay? So if it's pulling on one side more than on the other or something like this, then this equation will have a slope and then it gets non-trivial solutions, okay? So this is the first lesson we learn here, that it's really important that there are gradients in the system. Okay. Now we actually start using elements which we have defined before. So the first thing which bothers me here is this u, okay? So u should be replaced by strain. Because, I mean, all my arguments was in stresses and strains, okay? So I would like to replace this here because, I mean, everything should be formulated in strain, but it's simple, okay? So the idea is, if you remember how I defined it, basically the relative displacement, okay? And this is nothing else than the gradient in displacement, okay? So this is u at a position x plus delta x minus u of x. So this is the relative change. So I mean, basically I have one spring which is pulled to this direction, another spring which is pulled to another direction, and the difference between them, this is the difference between left and right, okay? So I have to take this divided by delta x. So it's really du dx. Okay, it's a very basic relation which we will use over and over again. But the strain is nothing else than the derivative of the displacement. Then I want to replace the n by sigma, okay? Because, I mean, I started with force. The reason is it's easier to say there are three forces they have to balance, okay, it's a force balance, but really we have stresses in the system, but that's easy, okay? So the stresses are simply these normal forces divided by the cross-sectional area, and not the constant here. I can put a spatially dependent cross-section, okay? But nothing speaks against this. So I basically bring this A to the other side, and then I put this into equation for n, and the epsilon I replace by 2, okay? And then we are basically done. Yeah, let me write it step by step. So dn dx, this is the left-hand side. So I replace the n by sigma times. Then I actually replace the sigma. Okay, I haven't written this yet, but you remember. The sigma I replace by E times epsilon. Okay. This is the material law. And I still have the A. And then I actually pull these two guys together. And how do I call them? Yes, C. This is what I call C from the very beginning, okay? And in principle, the Young's modulus could be a function of space. The cross-sectional area could be a function of space, so C could also be a function of space, okay? No reason not to write a X dependence here. And of course, this will always be a function of space. And then the next step would be, so now we have E in front, okay? And then the last step would be to replace the strain by the gradient in deformation, okay? And this would now be, okay, and this we have to equate to rho times U. Where actually, in general, also could be a function of X, okay? This is actually what we use in our model. So you could make everything a function of X here if you want. Problem is this. Okay, so if you now make this assumption that C is a constant, so this means constant cross-sectional area, constant Young's modulus, then we get a nice equation. Basically, it would be the constant C. This derivative goes here, so it will be second derivative. Then on the other side, we have this one, we put to the left. And then this is our equation. So this is now our main equation, which we are going to analyze the following. Maybe ask anyone reminded by some other equation? Does it look familiar to you? Yes, Yukawa, very nice. More suggestions? But from other parts of physics. What's about Poisson equation? Electrostatics, okay. So you have here the second derivative. It's the one-dimensional version of the Laplace equals, and the right-hand side you have some source, and the source happens to be linear to the U, okay, whatever this is, phi, okay, in electrostatics. So one of my favorite equations is the Debye-Hückel equation, right? So the Debye-Hückel is electrostatics where you have pluses and minuses, which basically balance each other, and then you get exactly this equation. So this is the Debye-Hückel equation. And now, having Yukawa and having the Debye-Hückel, you should immediately see that you get screening behavior and you get exponential decays. Okay, this is what these equations do for you. So again, the solutions will be somehow exponentials. Okay, without any analysis, you see that it will be always decaying functions. We are not talking about decays in time. And if you worry, what is the length scale here? You put together. So the way you could write this, let me write it like this. You could write it like this. Okay. And then you see that this lambda has to be C divided by rho square root of this. So this is the length scale over which the exponential solutions will decay. So I call it the localization length. Yeah, because I have this situation in mind with the cell being a contractile bar pulling on springs, okay? And then when I say, okay, there's a focal adhesion and the cell is pulling at some point, how far will this decay or this propagate into the system? And it will be on this length scale, okay? And this is similar to, if you know hydrodynamics, and we come to this in the third lecture, there is a hydrodynamic length. For example, if you cut the cortex or something like this, you have hydrodynamic decay lengths. Elasticity theory. Okay, so let me go through 3 examples or applications. I could skip to spare, it's not pedagogical. So I go through them, right? Yeah, okay. So my first application, so I go quickly, would be no springs, force pulling on right. Okay, so what I think about is I have a sort of wall to the left. I have a bar, no contraction, no spring force pulling on right, no contraction because I'm pulling from the outside, okay? And I'm pulling with the force F, okay? That's all. So this means no springs, rho equals 0, right? So I only have the, if you wish, the Laplace operator, second derivative equals 0. Then the boundary condition. So in principle, okay. So in principle, this means that U should be something like A times B times X, okay? And now we have boundary conditions. So the first boundary condition is that at the left, it's actually pinned to the wall, okay? This means this goes away. And the second boundary condition is that I'm pulling on the right-hand side with a force, okay? So this force, okay, sorry. This force is basically the normal force at L, where I now introduce the length of the system. But by this law here, okay, the N is nothing else than the derivative of U. Taken at L, okay? And this means that if I now do the derivative of U, okay, this is B. So I can now actually write what B is. B is F divided by C. And therefore, my U of X will be linear in X. It's just F divided by C times X. Okay, very simple. I'm pulling the right-hand side, linear extension, no extension here, larger and larger. Okay, that's easy. Now a second example. Now we introduce the springs. Okay, so the equation now looks like this. Wait, there was a minus. This is our equation. Or I can immediately, sorry, I can immediately write it with this, did I call it lambda squared? I can write it like this. Now the general solution would be exponentials. Okay. Thanks. That's why I always check my notes. Yeah. So now what I'm doing is I actually define the system a little bit differently. I basically put the 0 in the middle, okay? Because this way it's symmetric. And I can immediately use a symmetry argument. So again, there are these springs here. And I'm putting on the right-hand side. No, wait, this is wrong. I just keep it like it was before. Sorry. This is the same example, so it's still like this, okay? So the springs will all be extended to the right-hand side. Sorry. Okay, so I use, as before, that at the left is pinned at the wall. And this means that B has to be minus A. So if I put in the 0 here, it's 0 equals A plus B. Okay, B equals minus A. And this means that if you now put this here to minus A and pull out the A, you get a function which you all should know very well, which is which function? I don't hear anything. Yes, cosh, I heard it from here. Very good. So it's a cosh, right? So, no, it's a sinh. Sorry, it's the minus. Sorry, it should be the sinh. So we get U equals 2A sinh X over lambda, okay? And now we do the same idea with the boundary condition like before. So at the right-hand side, we are pulling with a certain force. So F at the right-hand side is C times U dash L. Okay, and this we can immediately get from here. So now comes the cosh, because we do the derivative on the sinh is the cosh, okay? So now we have 2A C divided by this lambda from the inner derivative cosh, and we do this at L. And now you can solve this for A, okay? So A is 1 over cosh. And then we put it together, and the solution will be F times this lambda divided by C divided by the cosh taken at L. And that's it, okay? This is the analytical solution to this problem. So pulling on a bar which is attached to a elastic foundation with a force F from the right-hand side, and you see that it's non-linear. So basically, if this is X, 0 to L, my extension, it basically grows from 0 because it's a sinh, okay? And it goes up like this. So the way I look at this is, I see that if I compare this with the other situation, okay? So example number 1 was like this, okay? So this is 1, and now we have 2. So if you compare, the difference is that the displacement and also the forces will be localized at the end, because the system is pinned, right? And it cannot really move on the left-hand side, so it moves on the right-hand side, whereas there's more slack in the system, okay? So what I see here is actually force localization. Because the force is always, we could write it here immediately, okay? The force on the substrate, so the traction force, okay, it is simply like here, okay? It's C times U dash L, U dash X. So it basically gives you also an exponential function. So what you see is that the largest, no, wait, this is actually, no, this is not what I want to say, sorry. I have to retract, okay? The traction force is rho times U, okay? So it's exactly this function, sorry. This was the internal force, okay? But the external force, which you see in the substrate, is just the displacement of the springs. So the traction force, the force on the substrate, this is localized to the right. Okay, 5 more minutes, then we are done. Because we now come to our last and most important example. because this is now our model for a contractile cell on an elastic substrate. Okay, that's exactly what we aim for. So this would be the contractile bar. Which means that the force is now coming from inside and not from the outside, okay? In examples 1 and 2, I was pulling from the outside, now I pull from the inside. So how do I do this? Yeah, so maybe I first write active cell mechanics, okay? We always write that the stress is the passive stress plus the active stress, okay? So this is what I already wrote earlier, so active cell mechanics. But honestly, I mean, this is just physics, right? I mean, I'm now talking about cells, but it could also be, for example, a metal which has been glued to a substrate and you lower the temperature and the metal contracts, okay? So if you look in Landau-Lifshitz, that's exactly one of his later chapters in the book. So we interpret it in the context of cell adhesion and cell contractility, but it really is a physics model for something which is contracting, and it could be any other effect, okay? So for us, of course, the rho at the sigma A, the active stress would be proportional to the chemical potential of the ATP hydrolysis, but it could also be the temperature difference between two metals, okay? So in general, it's a very, very physical concept what we're doing, nothing new if you wish, okay? So now how we do it, I basically translate this equation into my forces. So I write my normal force equals the passive force, and this is what we already had. So it's the one-dimensional modulus times the derivative of u. And now I add my active force, and I just call it P. Okay, so this is my active contractility. So remember what I said when I started all of this, I said I have this slice. And if I say there's an internal force, I always say it's perpendicular to the normals, okay? In the force balance, it's actually two forces, right? Now I write here a new element P for the internal stress or force, and this again is two forces, okay? Because in continuum mechanics, you always have sort of a little element which is pulled on all surface elements, and there are only two surface elements, and they're pulling against each other. So what we really have here is a force dipole. Force dipole. So if it was a force monopole, you would not couple it here. You would basically couple it as a body force, but not in this way, okay? So this is really a force dipole if you do it this way. Okay, so now our equation looks like this. So we have lambda squared second derivative minus first derivative. This is like before. And now we have a new element in the system. But the trick is that it, if you go from the equation for n to the equation for u, you have to do one derivative. Okay, so one sec. So on the right-hand side, I now have actually p dash divided by rho. No, I take it to be a positive number. No, that's why I take a minus here. Wait a sec. At this part here, yeah, good point. I'm not sure, right? But I mean, let me see. So basically, we can show that the P is the volume change in volume, and this should be negative. So I think it should be negative. Yeah, thanks. Okay, so now the equation is similar as before, but we have to solve it with this extra term here. Okay. Now, what comes to our rescue is that we now assume P equals constant. Okay, active stress constant. This is what we often do. We say it's basically the chemical potential of ATP hydrolysis, and this is basically constant, right? So with this assumption, the term drops out. Okay, And we are luckily back to number 2, so we don't have to do anything. We already solved it, right? So, I mean, in principle, the solution is clear, but there must be a difference, and the difference is in the boundary conditions. Okay, so first thing I say is that I now have U equals 2 times A times the sinh x over lambda. Okay, this is like before, but I don't determine the A in the same manner like before, but because now something is different, okay? So the way I determined A before is I was pulling on the right-hand side with a force. Now I'm pulling from the inside, and this has to be something different, okay? So what I now have to do is I have to go to my force balance. Okay. So no, what I'm really doing is the following. So I use this insight, which I explained before, that forces which are equal magnitude balance each other, okay? And because the internal force is constant, they balance each other everywhere, except at one point. And that's the right-hand side, right? Okay, so in the right-hand side, it's unbalanced. So yeah, so basically here the system is unbalanced. Okay, so now I ask, what is the force there? So the force here is the passive part. So it's C times U dash at L. And then it's the other part, the P. Okay, and now you see how it works. So basically, we set this to 0 because we have a free stress boundary condition. Okay, in the other example, there was a force pulling. Now nothing is pulling from the outside, it's only from the inside. Okay, so this is a free stress boundary condition. And with this, we actually can determine the A. So we have the U here. We have to take the derivative of U. This involves the A. And from this, we can extract the A. And then we put this back into our solution. So now I go to the last board. And our solution will be minus P times lambda divided by C, the sinh x over lambda divided by the cos L over lambda. And that's it. This is our analytical solution of the model. So if we now look at this, this is the point where I wanted to explain that I actually take the contractile bar now to be sort of doubled, okay? I mean, earlier I was pulling against the wall and I had E at 0 equals 0, sorry, U displacement at 0 equals 0 because there was a wall, okay? But now I double the system and take this to be a symmetry argument. So this is just the middle of the cell, okay? There it should be 0. Then I have basically the 2 stress-free boundaries left and right, okay? And then I have all the contraction inside. This is the P, okay? And then I have these forces, the springs which are extended and which are the traction forces, okay? So you see that if P was 0, no deformation. So the deformation is driven by the cell contractility P, okay? Then you see everything is on this length scale lambda. And of course, if the modulus of the cell was very large, then the deformation would be very small, okay? Now we actually plot this. So the sinh, let's say we go from minus L to plus L, and then the sinh would basically look like this. So it's linear if you are on a scale smaller than lambda. But if this cell is much larger than lambda, which usually is the case, okay, the cell is 10 micrometer, the lambda is typically a micrometer or something like this, okay, then you would see this slope in the curve, okay? So what you get is, again, this localization to the sides. So if you plot the traction force, it would be exactly the same curve, right? Because the traction force, oops. So this is displacement. So on the left, you pull to the right. On the right, you pull to the left. So this is what's shown here. then the traction force is just K times U. It's the same thing. Okay, so traction force just this times K, whatever you want to draw here. Okay, so this is basically force localization. And this is exactly what we measure in traction force microscopy. So all the forces are usually at the periphery of the cell, okay? And many people think, oh, it's clear, there are no focal adhesions. But the focal adhesions come sort of as a response to the system, okay? And the other way you can interpret this is that there is first adhesion, which is maybe many focal adhesions, okay? But the ones in the middle don't get any traction forces and then decay because they are mechanosensitive. And this is why in the end you only have them at the periphery. So the argument goes both ways, right? So I think this is not a bad model for this. So we have force localization at the site. And now another thing we can actually gain from this, we can look at the internal stress profile, okay? So the stress profile. Okay, and the stress profile is basically goes like the derivative, so it goes like a cosh. It looks like this. Okay, parabolic. And this is something which has been measured with monolayer stress microscopy. I don't have time anymore to introduce this, but it's the same ideas, okay, that you basically make a relation between traction forces and stresses. We already did this. This is exactly what this model is doing, okay? This is a sort of simple version of monolayer stress microscopy invented by Xavier Trippa. And what you get is this parabolic profile. And Xavier actually analyzed this for cell monolayers, which we can interpret as large contractile cells, okay, supercells made from many cells, but effectively like one big cell. And then he actually reconstructed it from his data, and he also gets this profile. I wouldn't take it as independent experimental verification because he uses the same theory, essentially, okay? But it's reassuring to see that people have extracted this stress profile from experiments for cell monolayers, okay? And I also have to say that this calculation has been done by Sheila, by our group, Christina Marchetti, Xavier. So many people use this kind of calculations in their work, okay? This is why I think this is really sort of a nice minimal model for a contractile cell adhering to a substrate and pulling it together. Yeah, questions?
How do the stress is localized in the internal of the cell while the force is localized of the exterior?
Well, this is the way it is. You have to think about the definitions, okay? So this is the force inside the contractile bar. And it has to go to zero because you have zero stress boundary conditions, okay? So you balance the forces against the substrate, but here at the sides, it has to be zero, okay? So it's clear that it has to look like this, okay? But on the other hand, the displacement is related to this by the derivative. And therefore, it can have another shape. It's not the same thing, yeah? But it's important to understand that these traction forces we can measure with elastic substrates. These forces, we would measure them with laser cutting. So we basically take the bar, cut it in the middle, and then we have two bars, each relaxing by itself. And then we should see a signature of this. Okay. Yeah. So everything remains. So yeah, we wrote down, of course, and Sheila also, we wrote down the full equations and are there in my notes, but I'm not sure if I will be able to show them. So in principle, if you go to higher dimensions, 2 or 3 dimensions, the first thing which happens is that you get more elastic moduli, okay? But if you stay with the isotropic linear approximation, you only get one more, which is the Poisson's ratio, and this is always 0.5. So it doesn't make a big difference. However, if you now say that this is a more complicated system, like a nematic, you have to introduce a nematic order parameter field, the Q tensor and things like this. So then, of course, it gets more complicated if you give it more internal structure. But if you stay on this linear isotropic level, This is just the 1D version of the full model, and the full model is not so different, okay? And for 2D, we wrote down the solutions. It's basically Bessel functions and Airy functions. And 3D, we don't care because the cell is always flat, okay? But in principle, it should again be some kind of Legendre polynomials. I mean, it's really like solving a Laplace equation in the end, yeah. Okay, more questions? Yeah. So wait a sec before you finish this. So I prepared some slides and I put them on the Google site. So I'm not sure if I'm going to be able to show them. So these slides show traction forces as we measure them. It actually shows again this model, and it shows that this is in very nice agreement.